So we know we want to do this general change of variables, substitution and multiple integrals. There's one computational tool that we need to be able to do this, and let me show you the definition of it right here. The Jacobian determinant, or for short, we'll frequently just call it the Jacobian of the coordinate transformation, the map x is g of uv, y is h of uv, is j of uv, is defined to be the 2x2 determinant of these four partial derivatives. Partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. So it's this times this minus this times this. So this times this minus this times this. Well, we write this j of uv. Sometimes we write it in this form, partial of xy divided by partial of uv. That's suggestive of how to fill in that determinant. Okay, so in the next video, we'll see where this comes into play, how we use this. But before we do that, let's just practice computing the Jacobian in some small examples here. So take a look here. Compute the Jacobian. So the change of variables, g of uv is 4u minus 3v, 7u plus 2v. So note here, this is a linear transformation. Okay, so in this case, j of uv is defined to be, so the first partial derivative here, so of course this corresponds to x, and this corresponds to y. X and y down there. Partial derivative x with respect to u is 4. Partial derivative, so I'm using this here. Partial derivative x with respect to v is -3. Partial derivative of y with respect to u is 7. And partial derivative of y with respect to v is 2. So this is 4 times 2 is 8 minus 7 times minus 3. 8 plus 21 is 29. Note here that this is a constant, and that's not an accident, excuse me. When we have a linear map like this one, we will get a constant. Now, for the Jacobian, this does not depend on u and v. However, we should not be surprised, and in general, it will depend on u and v. So let's do this example down here. So we need the partial derivative of this with respect to u. That's v over 4. Then the partial derivative of this with respect to v. That is u over 4. Oops, there shouldn't be a comma there. Then we need the partial derivative of y with respect to u. So this is going to be -2v over u cubed. And then the partial derivative of y with respect to v is 1 over u squared. So this times this minus this times this, v over 4 times 1 over u squared minus -2v over u cubed times u over 4. I think that simplifies just a smidge. V over 4u squared minus, minus times minus is plus. That u cancels with a u downstairs, so I think we get 2v over 4u squared, so 3v over 4u squared, though I haven't made any mistakes there. Okay, so that's two relatively straightforward examples. Let me show you one more example here. Compute the Jacobian for g of r theta is r cosine theta, r sine theta. So now instead of using u and v, we're using r and theta. This should be ringing a bell. This looks like a, polar coordinates. Okay, so let's do j in terms of r and theta here. So it's going to be 2 by 2 determinant here. Okay, so first we have the derivative of this with respect to r is cosine theta. The derivative of this with respect to theta is going to be negative r sine theta. The derivative of y with respect to r is sine theta. The derivative of y with respect to theta is going to be r cosine theta. And when we do this determinant, cosine theta times r cosine theta is r cosine squared theta minus sine theta times negative r sine theta is negative r sine squared theta. So this is r times cosine squared theta plus sine squared theta. And we know, of course, that this is 1. So our answer here is r. So what is the Jacobian for the polar coordinates transformation? It's r. Now think about this. Is there anywhere when we're doing integration of polar coordinates where a factor of r just appeared out of nowhere? Think about that. We're going to be talking about that in our next video. Okay, so I want to wrap up here. This is how to compute Jacobians using this formula. We'll see how to use the Jacobian in the next formula. Let's end this with a pre-class problem. Just have you compute the Jacobian here for this change of variables, this map.